All right, we're going to start section 7.3 here. This is actually the first section in chapter 7 that begins to introduce logarithms. You'll want to make sure that you have your graphing calculator with you and handy because we are going to be using a logarithm button on your calculator that I'm going to walk you through here. Okay, I think one of the things that we want to keep in mind, because logarithms are generally a pretty difficult topic for students, and today we're just going to be getting kind of introduced to what a logarithm is and how they can be helpful when we're solving certain types of equations. Okay. So here's what logarithms are used for. Logarithms are used to find unknown exponents in equations. Okay, we've been studying the last two sections, we've been looking at exponential equations. Exponential equations are equations like what you're seeing here. Okay, you'll notice all 5 of these equations are exponential equations, and that is for the simple fact that the variable, your exponent, is what's missing. Okay, that's where the variable is located, in the exponent. Okay, and so this is where logarithms come in. They can be quite helpful with trying to solve equations when your variable is kind of stuck in the exponent here. Okay, so let's look at these 5 equations and see if we can, at least for the first few, try to reason through what we think the value of x would be, and then we'll work our way all the way to those that are on the right here. So for example, in the first equation, 10 to the x power would equal 100. That's probably an equation that we could just think through, use some common sense here to think of what that missing exponent's value would need to be in order to make this equation true. 10 to the what power would equal 100. Of course, we know 10 squared would equal 100. Let's move to the next one here. 10 to the third power would equal 1,000. Now this one's a little bit more challenging, but I think we could reason our way through here. 10 to the what power would equal 1 over 100. Well, if we think of our missing exponent here, and it equals 1 over 100, okay, let's see if we can rewrite the 100 as 10 raised to a power. We know that would be 10 squared. And then we're going to pull that 10 up to the exponent, up to the numerator. That way, the two base values, 10 and 10, are the same. Okay, this is something similar to what we did in the previous few sections here. Okay, and then we could simply set their exponents equal to each other. So that means the missing exponent on the 10 would have to be a negative 2. Okay, that one was a little bit more challenging. But when you look at examples 4 and 5, these feel really difficult. How to figure out what the missing exponent on the 10 would be that would equal exactly an 85 or exactly a 2.3. Okay, we know that 10 to the first power equals 10. If we do 10 to the second power, like this example over here, well, that would equal 100. So it kind of feels like this exponent should be somewhere between 1 and 2. Okay, it's probably going to be some decimal. Now, we could guess and check our way to getting somewhat close to what the missing exponent is. But these two problems here are where logarithms would be very, very helpful. So we're going to skip those two examples here for the time being, and we're going to come back and revisit these after we've been introduced to how logarithms work. And I think we'll be able to see how logarithms make solving these two equations pretty easy. Okay, so when you're dealing with logarithms, you can write a logarithm as an exponential equation that is in logarithmic form. Okay, so we want to kind of think of it as we have two forms here. Okay, we have exponential form, which is when we have a base number, we're calling that b here. When we have an exponent, okay, that's x, okay, and then it equals a number here. Okay, when you switch from exponential form to what's called logarithmic form, it's almost like this is a puzzle, or when you translate from one language to another, kind of each piece kind of translates to a specific spot. So for example, your base number in exponential form is actually what we refer to as the base of your logarithm. Okay, so I'm going to kind of color code this here. Okay, this would be our base. In the logarithm, it's often written as a subscript, a very small number written underneath where you have the log. Okay, we call that, again, the base. Of course, we know that we would refer to the x here as the exponent. If you look at where the exponent gets placed in logarithmic form, it gets placed on the other side of the equation by itself. Okay. Finally, the y is what we call the argument of your logarithm. Okay. Now, ideally, your logarithm would have numbers in it. Like, for example, maybe we say log base 5 of 3. Okay. The 3 would be considered to be the argument, and the 5 would be considered to be the base. Okay. All right, so let's see if we can try to take equations that start out in exponential form, and we're going to convert them into logarithmic form. Okay, we're going to convert them into logarithmic form. So we want to just make sure we get the pieces in the right spot here. I always like to grab the base, which we know is the 5 here, and we're going to write that log with a little tiny subscript 5 for our base. Okay, if you look back up here at this little chart, whatever your exponent is, which was the 3 in this example, that's going to be placed over here on the other side of the equation. So I'm going to be placing the 3 right there. Okay, and then the number that's on the one side of the equation by itself in exponential form, that's our 125, that becomes what we call the argument of the logarithm. So we write that normal size 125 here. Okay, I want to talk through with you how the proper way is to read or pronounce logarithms. The correct way to read this would be to say 3 equals log base 5 of 125. 3 equals log base 5 of 125. Okay, so we're going to go ahead and try this next one here. We want to practice writing this in logarithmic form. Okay, if you want, you can pause this video and go ahead and try to do it yourself, and then you can unpause and check and see if you did it correctly. Okay, so I'm going to start with the base number. That would obviously be the 7 here in exponential form. So I'm going to do log base 7. The exponent, the -2, that's what I'm putting right here on this side by itself. And then what that equals, the fraction 1/49th, that is actually the argument of the logarithm. Again, the proper way to pronounce this would be to read -2 equals log base 7 of 1/49th. Okay, let's try to go the other direction now. On these 2 problems down here at the bottom, you can see these are starting out already in logarithmic form, and we're going to convert them into exponential form. So we're starting here, and we're working our way over here to kind of put it back in exponential form. And again, I like to start with the base. Okay, so I can clearly see the base of this logarithm is a 3. So that means when I'm writing this in exponential form, 3 will be my base number. Okay, knowing in logarithmic form, the value over here, the constant that's by itself on this side of the equation becomes the exponent in exponential form. I'm going to be putting this 4 as my exponent on the 3. Okay, the argument of your logarithm, which is the 81 in this example, that is what will then go on the other side of the equation in exponential form by itself. Now, when you're going this direction, it's pretty easy to check to make sure that you did this correctly, because the result should be a true equation. Okay, 3 to the 4th power, if you type that into your calculator, that should equal 81. Okay. All right, so let's go ahead and try this next one. Again, if you want to pause the video here to go ahead and attempt to put this one in exponential form first, and then you can unpause to kind of check and see how you did. The base on this log is 2. The exponent I'm going to place on the 2 would be a -5, and I should set that equal to the logarithm's argument, which would be the fraction 1/32. Again, pretty easy to check if you just type in 2 to the -5th, and then you could also type in the fraction 1/32, and those two should be the exact same decimal. Okay, now that we've practiced switching from exponential to logarithmic form and from logarithmic form back to exponential form, let's go ahead and take a look at how to evaluate like what number these logarithmic expressions are representing. Okay, a logarithm represents a number. Okay, and these examples that we are going to go through here, and I have this 4th one just kind of worked out for you so you have an extra one to look at. These are exactly like problems 7 through 12 on your worksheet. Okay, so they're very, very similar. You would want, if you're struggling with those problems on the worksheet, these are the examples you would want to look back at in your notes here. Okay, so the steps are typed right along the side here. The very first thing you're going to want to do is you're going to want to set this expression equal to y. Okay, our goal here is to try to figure out what value, what number does log base 4 of 1/64th represent? And so we're setting that equal to y here. And if we can figure out what number y equals, we'll also know the value of log base 4 of 1/64. Okay, so now that I have it set up as an equation, we can take what we learned on the previous page, we can switch this from logarithmic form into exponential form. Okay, and if you need to go back and scroll to kind of look back either at these examples that started out in logarithmic form here and we switched into exponential form, or just to use this chart till we get the hang of it, we're going this direction, starting in logarithmic form and backing up here into exponential form. Okay, and so I'm going to always start with the base. The base is 4. My exponent would be the y, and that would be set equal to the argument 1/64th. Okay, and then I'm going to kind of treat this similar to how we worked with the exponential functions in the first 2 sections of this chapter. The goal was to try to manipulate the 2 sides here so that we can make the 2 bases look exactly the same. If we can make these 2 bases look exactly the same, then their exponents would have to be equal to one another. Okay? Anytime you're dealing with a fraction, it's a good idea to take the denominator of your fraction and see if you can write that denominator using the same base number that you have on the other side. And so you want to ask yourself, can you manipulate a 64 and make it look like a 4 raised to a certain power? Okay? And we certainly could write that as 4 cubed. Okay, but we do need everything pulled up into the numerator, so I'm going to pull that 4 cubed in the numerator, and that's going to change my exponent from a positive 3 to a negative 3. So now I have 4 to the y power equals 4 to the negative 3rd power. I can simply take the 2 exponents, and I can set those equal to one another since their bases are the same. Okay, and there I've discovered that the value of y is negative 3. Now, if you look back at the original problem, we had set that expression equal to y, and so essentially what we're saying here is that log base 4 of 1/64th is equal to the value negative 3. Okay? All right, let's go ahead and try a second one here. We're going to start with, the steps are listed off here to the side, but we're going to set it equal to y. You can see that step number 2 then asks you to switch the equation into exponential form. That will be 6 to the y power equals 216. Okay, and then what we want to try to do is we want to try to manipulate this so that we can get both of the bases to be exactly the same. So generally, the rule of thumb is you want to manipulate the larger number. Unless you're dealing with a fraction, then you want to try to manipulate the denominator of the fraction and then pull it up like we did in the first example. So you can fiddle on your calculator and see if the number 216 can be expressed as 6 to a power. Okay, we know 6 squared is 36. We can try 6 cubed on the calculator, and I believe that's it. If you type in 6 to the 3rd power, that is the same thing as 216. Okay, we write it like that. We can see now our bases are both equal to each other. If the bases are equal, the exponents also must be equal. Once you solve for y, the value of y, in this example 3, is what the value of log base 6 of 216 is. Okay. All right, let's try example C here. Okay, in example C, we're going to set it equal to y, and then we're going to change this into exponential form. This will be 32 to the y power equals 2. Okay, now this one feels a little bit different, but what is the same is you should always be trying to manipulate the larger number. Okay, again, unless you're dealing with a fraction here. Okay, so I want to try to write the number 32 as 2 raised to a power. Now, I understand that there's already a y here in the exponent, so what you're going to want to do is put a set of parentheses where the 32 is. Go ahead and put the y on the outside of the parentheses as the exponent that's on the 32, and then inside the parentheses, express the number 32 as 2 raised to a power. And again, you can try on your calculator 2 cubed, that's 8, 2 to the 4th power, that's 16. I believe it's 2 to the 5th power that'll get you 32. Okay, so you're just swapping the 32 out for a 2 to the 5th. Okay, what we will do next is we will go ahead and multiply our two exponents together here, the 5 and the y, and now the left side is 2 raised to the 5y power. I'm going to go ahead and show that the exponent on the 2 on the right is a 1, and now we have the two bases are the same, so that means the two exponents must also be equal to each other, and now when I set them equal to each other, I have this added step here of just needing to solve this little equation for y, and I discovered that the value of y, hence the value of log base 32 of 2, would hold the value of 1/5. Okay? All right, so there's something called a common logarithm, and this is the button that's actually on your calculator. I'll show you where this is at here in just a moment, but what a common logarithm is, it is specifically a logarithm that has a base of 10. Okay, when we deal with logarithms, the base of a logarithm can be any number, okay? 10 is what we refer to as a common logarithm. And so you can see here in this example, the directions are to solve each equation for x. Okay, now clearly these are both exponential equations. I don't even see a logarithm in these. Okay, I can tell that my variable is in the exponent, so that's giving away that these are both exponential equations. Okay, we're trying to figure out what needs to be this missing exponent that would cause this to equal the value that we have on the other side of the equation. Now, these are really, really similar to the two examples on the front of the notes page that we initially chose to skip because they didn't feel like we could easily sort of reason our way through what that number would be. Okay. Now that we've learned a little bit about logarithms, let's see if we can't use logarithms to help us find the exact value for these missing exponents here. Okay. And so what we've learned is that really logarithmic form and exponential form are kind of what we would call inverses of one another. If we have an equation in exponential form, we can easily convert it or switch it into logarithmic form and see if that's helpful in any way for solving the variable that we have missing. So I'm going to take this equation, and again, if you reference back to the front of the notes page, that's where we had this little diagram here. Now these equations are starting out over here in exponential form. We're wanting to put all these pieces over in the spot that they would land to put them in logarithmic form. So here's how this would look. Again, I'm going to start with the base here. Okay, so I'm going to do log, my base is 10. The exponent goes over here by itself, so the x goes there, and the argument of the logarithm is that 0.0054. Now, if we look closely here at this, I can tell that this would classify as being what we called a common logarithm, and that's simply because the base on your log is a 10. Okay, now if you have your calculator there, you can see along the left-hand side of your calculator, it's actually the button that is immediately to the left of the number 7. It should read log, log on it. Okay, when you press that button, you'll notice it doesn't show you what the base of the logarithm is. It immediately feeds you a left parenthesis. It wants you to type in the argument of the logarithm, and in this case, the argument would be this 0.0054. Now the assumption is when you use that button on your calculator, it is a common logarithm. So while you don't see the 10 as the base, it's implied. Very similar to when you use the square root button. It doesn't show you a 2 as the index, but it is implied that there is a 2 there. So you're going to press that button and then go ahead and type in 0.0054 and hit enter. Okay, now this is a decimal that will keep going on and on, so for the purposes of us writing it on our paper, we're going to have to round it to 2 decimal places. However, the whole decimal that you're seeing on your screen is actually what the true answer is here. Okay, and it's not going to let you use the math fraction button and switch that back into a fraction, but we could check our answer. If you were to type in 10 and then hit the caret key, and then if you were to hit the second key and the negative button, okay? What you're selecting there is you're selecting what's short ANS for answer. It'll take that previous answer, the whole entire decimal, it'll use that as the exponent of the 10, and when you hit enter, it should come out that that is exactly 0.0054. That's just a quick way to check it. But we would write on our paper, just rounding that approximately that missing exponent would be negative 2.27. Okay, so let's try the next one here. We're going to switch this into logarithmic form. I can see again that this is great, that the base is a 10, because that's going to allow me to use that common logarithm button on my calculator. I'm going to press that log button. I'm going to type in the argument of 12, and I'm just going to round my answer to 2 decimal places and circle it. Now, if you're wondering, that's nice, but what if the base on my log was something other than a 10? How would we do that? Well, we will learn that in the next section, but for now, any of these problems that you're going to be asked to do like this, you can assume that you're going to be given where it's going to be set up where the base is 10. Okay, so let's go ahead and flip back to the front. See if we can now answer these 2 problems that we initially skipped because we thought they were a little bit too challenging here. Okay, I do ask that on your homework, you do need to be writing down on your paper what it is you are pressing in your calculator. And so for that reason, on problems like these 4th and 5th one here that we skipped initially, I need you to write down on your paper how that equation would look in logarithmic form, because then that is showing me that this ultimately is what you are typing into your calculator. You will press log and then 85 as your argument, and then you will round that to 2 places. That will be 1.93. Okay, but this part right here that I'm highlighting, that has to be shown on your paper. Okay, let's do another one here. X equals log base 10 of 2.3. We're going to press the log button, 2.3 as our argument. We're going to round that to 2 places. 0.36 would be our answer. And again, this part right there that I highlighted, that has to be shown on your paper. That's showing how you got those decimals that you're writing down. Okay, the last thing is just, once again, this recurring topic that keeps popping up in just about every chapter, revisiting this notion of transformations. And so our parent function is just going to be log and whatever the base is in the problem of your argument. So your base has no bearing on your transformation at all. Okay, you're only looking at the numbers that are on the inside, if they're inside the parentheses, or numbers in front, or all the way on the end here. Okay. All right, so if you look at A and B, you'll notice the difference is, on example B, this minus 3 is included in the parentheses. If you look at example A, this plus 1 is not. Now, the example I did for you, you can tell the minus 5 is on the outside. That's why I said down 5. The plus 1 is on the inside. That's why I said left 1. Okay, on this example, since this plus 1 is not included in the parentheses, it means that plus 1 is considered to be on the outside of the function. So you should be identifying that as moving the graph up 1 unit. Okay, the 3 that's out in front, we would call that a vertical stretch. The stretch factor would be 3. Okay, moving to part B, the 1/2 would be our vertical shrink or vertical compression, shrink factor 1/2. Okay, again, you're not doing anything with the bases at all, but to address this minus 3 that's on the inside, that would be a shift to the right 3 units. Okay, everything that you're going to be asked to do on this worksheet 7.3a, there should be an example very similar to it on this notes page. So feel free to rewatch any of the examples or at least look back at your notes if you are struggling with any problems on the worksheet.